Hello guys, and welcome back to Science Why, and thank you for clicking on the video. As you can see behind me, it's quite a sunny day today. Still really chilly though, and that's why we've just got the heating on at the moment just to warm things up a little bit. Which leads me to this thought: why do houses have these little vents on the outside of them? What are they for? What is their purpose? Let's look into it. Okay guys, so you probably already figured out that that vent that we see in the outside of the house there is actually coming from the boiler. Okay, and the steam that you're seeing, because it's quite a cold day, what we're seeing is the vapor condensing to become water. So we're seeing that steam, which is basically condensing water vapor. And the reason we see water is because, of course, water is one of the two products of combustion: water and carbon dioxide. Water is the one that people tend to forget about, so worth remembering. All right, and what we'll look at in a bit more detail later on in the video is the difference between complete combustion and incomplete combustion, because as well as allowing the water vapor out and also any toxic gases that could be produced during the process of burning the fuel, that then also allows oxygen to come in order for the complete combustion to happen. So it's really important with a gas appliance that you have a good supply of air getting into the appliance, so that you have real proper combustion and complete combustion of the fuel. Otherwise it could be dangerous. And it's because of this, guys, that we need one of these in our house if we have a gas appliance. And this, of course, as you can see, is a carbon monoxide alarm or carbon monoxide detector. And the reason we need that, guys, is because carbon monoxide can be released if there is incomplete combustion. Now remember, with incomplete combustion, that's when you get lots of soot as well, potentially. So when you have a fire that has a very dirty yellow flame, it tends to produce a lot of soot, which is when you see a fire like a bonfire, or unfortunately if someone has a house fire, you tend to get an awful lot of soot and smoke produced. You are seeing a lot of incomplete combustion, and that's when you get those poisonous gases like carbon monoxide. And it's also the reason why, if you have a barbecue, you shouldn't have a barbecue or any flame inside a tent if you're camping, because that carbon monoxide can be released. Now, a really good example of incomplete and complete combustion is from the Bunsen burner. You'll be familiar with the yellow flame with the air hole closed, but with the air hole open, the blue flame allowing more oxygen to get to it, this would be complete combustion. So our yellow flame is incomplete combustion and the blue is complete. And this is why with some boilers there's a little tiny hole in the front to be able to check what we call the pilot light. If that light is blue, then the boiler is working properly. So we're going to have a closer look now at the actual equations for combustion. And first of all, complete combustion, we're going to have a quick look at how to balance that equation. Okay, so our word equation for complete combustion is methane plus oxygen gives carbon dioxide and water. Now the first thing we need to do is to write that as the symbol equation: methane CH4 plus oxygen, which is O2, never exists on its own, it's always O2. That gives us our CO2, carbon dioxide, and of course our H2O, water. Now, when you're balancing equations, what I find useful to do is make it really clear the distinction between the left side and the right side of the equation. There needs to be the same number of atoms of each element on either side of our equation. So a good piece of advice is to really clearly write out what you have either side, how many atoms of each. So we have one carbon on the left from the methane, 4 hydrogens also from the methane, and then we're going to have 2 oxygen atoms from our O2. On the right hand side, we've also got 1 carbon from our CO2. If If you count the hydrogens, we've got 2 hydrogens there from our water, H2O, 2 oxygens from the CO2, and a further oxygen from the H2O, because the 2 is for the H, not for the O. And that equation you can clearly see is not balanced. We need another oxygen on the left and 2 more hydrogens on the right. So how to balance it? Well, we're only allowed to put numbers before the molecule. So if I put a 2 here to say we've got 2 oxygens, for example, that gives us 2 further oxygens on the left because we needed more. Although we do actually have 3 still on the right, but we need more hydrogens. So if we put a 2 before the H2O, that is how we get our extra 2 hydrogens. There are now 4 hydrogens on the right to balance the left. But if you count up the oxygens again, because we've got 2 H2Os, we now have our extra oxygen on the right, and this equation now balances. Really simple experiment I tried with a candle that I found here. You just light a candle. A candle, because it burns with incomplete combustion, is going to produce some soot. So you can see the effect it has on this white bowl. So to summarise incomplete combustion, guys, you still get burning, you still get a flame, you will still produce water, but what you won't get is carbon dioxide. You would get carbon monoxide instead, which is poisonous, and also you often can get soot as well. So where else can you get pollution? Car engines. So another problem you need to know about, guys, is that of nitrous oxide. Now, as you may know, the atmosphere is 78% nitrogen, and usually nitrogen doesn't do very much. It's very inert. But when it's very, very hot, the sort of temperatures you get inside an engine, for example, around about 100 degrees C, a little bit over 100 sometimes, an awful lot of pressure in these engines as well. Now, as you can see here, it says turbo, and it's a multi-air system on this car, which is an Alfa Romeo. What the turbo does is it forces extra air into the engine in order to achieve more power.
I feel the need for speed.
But because it's forcing all that oxygen into the engine, and it's very hot in the engine, and the pressure's also very high, by the way, what that's likely to do is cause the nitrogen in the air to react with oxygen in the air because of the heat, and that produces what we call nitrous oxides. So if you look closely here at the temperature gauge on the car, it shows that the engine temperature can easily get up to 100 degrees, even as far as 130, and that's more than enough for nitrous oxides to be produced. And another problem that we get with fossil fuels when they're burnt is that we form sulfur dioxide due to the sulfur impurities with the fuel, and when that burns, the sulfur reacts with oxygen, and that's how the sulfur dioxide is made. So we'll have a little look here at how that sulfur dioxide forms when the sulfur reacts with oxygen to produce sulfur dioxide, which is SO2. No need to balance this one. Now that sulfur dioxide, the reason it's a problem is because it actually goes up into the atmosphere and it mixes and dissolves in the rainwater in the clouds, and that results in a weak sulfuric acid forming, and that's why we end up with acid rain, and that's rain that's slightly more acidic than it should be. The nitrous oxides as well will have the same effect. Now, nitrous oxide can be in different forms. It can be NO2 and NO3. So as a rule, we just call it NOx because that encompasses all of the nitrous oxides you can get, which is why we call them nitrous oxides. Those can also react with water, this time to produce a weak nitric acid, which again goes up into the atmosphere, reacts with the rainwater, and makes the problem of acid rain even worse. This diagram just summarises. As you can see, you've got nitrous oxides there on the right, sulfur dioxide as well. Those will both go up into the atmosphere, mix with the rainwater, and then on the left you can see acid rain. So what effects does acid rain have? Well, one of the things it can do is affect masonry, buildings, brickwork, particularly ones that are made out of limestone. Less so this kind of brickwork, but you will sometimes see this brickwork wearing away, which can be the result of acid rain. Acid rain can also affect trees, and what you'll notice sometimes is at the tops of the tree, the younger parts might be missing some leaves and look a bit dead, and that quite often is a result of acid rain as well. And another effect of nitrous oxide is what you see in the picture, which is called a photochemical smog. And it's where the nitrous oxides in the air will combine with other pollutants to create this really thick fog. And an interesting example of that was looking at pictures of London before and then just after the lockdown had started, and you can see these pictures in a very similar place, a total difference in air quality. And nitrous oxide can lead to problems with the breathing system, such as, for example, bronchitis.
Ain't nobody got time for that.
So that's about it for this video, guys. I hope that has been of some use to you. I'd just like to say thank you for watching the video to the end if you've put up with me and got this far. So until the next video, guys, hope to see you on that one. Hope to see you again on Science Why.